on YouTube also, sir.
Okay.
Sir, you can start the session. We are on.
But I have to answer questions, right?
Yes, sir.
How do I see the questions? It will be in the chat box.
In the chat box, sir.
Okay, okay.
And I saw 2 questions in this thing, Google Sheet, Google Forum. I'll just copy and paste it here in the chat box.
All right.
So you can start the session with that question.
Sure, sure.
Yes, sir.
So can you tell me about the exam pattern? All the questions are objectives or multiple choice type? Yes, the questions are all multiple choice types, objective. What are the career paths for becoming a device engineer? It's a good question. If you want to work in industry, then in India, semiconductor fabrication is not as much mature, so it's only starting off now. But there are many fabulous design houses that work on designing the devices, designing chips. So if you have an master's degree, for example, in device engineering, you can apply to different companies like Samsung, Global Foundries, Applied Materials, SanDisk, Micron, many of the companies that work on memory technologies like flash memories and all. They also need device engineers. People need device engineers in analog design also. So there are many opportunities for that. Of course, if you go abroad for your master's or PhD, then the opportunities are much more, especially in the US and Europe. There are a lot more companies that also work on fabrication aspects and other things, So then the opportunities multiply. But even in India, with the push from government, there should be more companies coming up on the semiconductor fabrication side. So there are many opportunities. I mean, I think we are at a point where there will be a lot more opportunities that will come up even in India now. Okay, in fabrication and experimental side. But that being said, fabulous design houses, as I already mentioned, they do have requirements of device engineers. And if you specialize in both device and circuits to some extent, then you can you can apply or you become eligible for a lot more openings in industry. Okay, I think that answers the question.
Good morning, sir.
Yes. Hello. So some questions could be asked in YouTube live also. I don't have access to that. So whoever is moderating, may I request you to please, if there's someone asking question on YouTube, you may.
Yes, sir, I'll share the question, sir.
Sure. Sir, Schottky barrier की equation में doubt है. What is the specific doubt? I need to know the doubt. So the question is, Schottky barrier height is taken in joule, but built-in potential is volt. So this is a confusion because of the energy and voltage. Barrier is energy, conduction band, valence band, they are all energy, but the voltage drop is potential. Potential drop is voltage. Okay? So when then the way you convert one from the other is by multiplying the electron charge Q, which means if you have a voltage of V, if you multiply by the electron charge Q or E, then that you get the equivalent electron volt, okay, in joule. I mean in energy. It's not joule, it's electron volt. You can convert electron volt to joule. It's the same energy, but it's the unit. You have to convert it. So for example, if you have a Schottky barrier height of 1.1 electron volt, that is energy, but the equivalent potential would be 1.1 volt. Not the built-in voltage. The built-in voltage will be the Schottky barrier height minus the conduction band and Fermi level difference. So anytime we talk about voltage drop, it's a volt. You multiply that by Q, the electron charge, you get the equivalent amount in energy. Okay, so that's how we convert from one side to another side. Okay, there are two different physical quantity, but they're related by Q, the charge. Then there is a question in an LED, electrons and holes recombine. Then after that, what literally happens to them in the depletion region? When electrons and holes recombine, that means they no longer exist as electron and hole. They have, if they recombine radiatively, that means whatever energy they have given it away in the form of a photon or a light. So that's what happens literally. The energy of the electron hole, they dissipate as a photon or as a light. If it is non-radiative, they will go into traps, or you may you have non-radiative recombination, emit as a phonon or whatever. Okay, so that's what happens. I hope that answers it. Yes.
नमस्ते सर। सर सबसे पहले तो सर बहुत बड़ी रेस्पेक्ट सर आपको, आपके कारण सर इलेक्ट्रॉनिक्स में बहुत इंटरेस्ट आया सर। मैंने अभी यूट्यूब पे क्वेश्चन पूछा था, अब मैं जूम पे आ गया सर। जो ये शॉर्टकी बैरियर की इक्वेशन लिखी थी अपन ने लिखा था 5b इक्वल्स टू क्यू वी बी आई प्लस के टी बाई क्यू एंड एन सी बाई एन डी, जो ई सी माइनस ई एफ था। सो सर जब हमने क्यू वी बी आई लिखा तो वी बी आई का फॉर्मूला होता है क्यू एन डी डब्ल्यू डी स्क्वायर अपॉन 2 एप्सिलॉन नॉट इनटू ए एस। तो जब हम वीबीआई की वैल्यू पुट करेंगे शॉर्टकी बैरियर वाले फॉर्मूले में, तो सर चार्ज का स्क्वायर हो जाएगा।
वो एक्स्ट्रा क्यू शायद टाइपो हो सकता है। एसेंशियली आपको देखना होगा एट एवरी इक्वेशन, एट एवरी क्वेश्चन, आर यू सेटिस्फाइंग द डायमेंशनलिटी। जैसे शॉर्टकी बैरियर हाइट में इफ द बैरियर हाइट इज इलेक्ट्रॉन वोल्ट, देन यू हैव टू मल्टीप्लाई द बिल्ट इन वोल्टेज विद क्यू, बिकॉज बिल्ट इन वोल्टेज विल बी वोल्ट, जैसे 1 वोल्ट या 1.1 वोल्ट। सो यू हैव टू मल्टीप्लाई दैट बाय क्यू, तभी तो ये जाके इट विल बी एनर्जी, इलेक्ट्रॉन वोल्ट। Am I making sense? So, and then the rest of the term जो है, the difference of the Fermi level and the conduction band, that is energy. So that will be just kT into ln of whatever. You don't have to divide it by Q if it is energy. If you want to convert it into volt, then you have to divide by Q. वो voltage और energy में Q का conversion है. Just make sure that there is no extra Q or a Q less. लिखने में शायद I may have a typo, but in general that is the fun.
कंफ्यूजन यही हो रहा है कि इसमें इक्वेशन में लिखूं क्या?
Okay, so the Schottky barrier height, if you denote it by phi b, and if you say that phi b is in electron volt, then you just write phi b equal to Q times VBI, where VBI is in voltage, volt. So you are multiplying by Q. Okay, so Q VBI plus KT, KT is energy in electron volt. Okay, KT into ln of whatever that term. Okay.
Okay.
Good morning, sir. Sir.
Yeah, your voice is little. Yeah. Hello.
Now I am listening, sir. Good morning,
Yes.
sir.
Yes.
Hello, sir.
Yeah, I can hear you.
Sir, one assignment question. Yes, sir. One assignment question was, sir, Schottky barrier height of independent of doping. Sir, if I consider Schottky barrier height is depend metal function minus of semiconductor work function, then semiconductor work function will be changed when the doping change. But sir, Schottky barrier height you say independent. How it is independent, sir?
Schottky barrier height is independent of doping. Yes, because Schottky barrier height is independent. A second. So I should have drawn that. I don't have a whiteboard here. What is the question? The Schottky barrier height is independent of doping. Is that what I'm saying?
Yes, sir. Independent of doping. Yes, sir. How it is possible, sir? I little bit confused, sir.
Oh, okay. Yeah. So Schottky barrier height is independent of doping. Yes, that is true. So when you form the Schottky barrier junction, you have to bring the Fermi level to align with each other. You understand that, right? So suppose the Fermi level of the semiconductor is at a higher level, you have to pull it down to align it with the Fermi level of the metal. That much I hope you are correct. You know it. Now the point is the barrier height. The Schottky barrier height is given by, ideally, the difference between the how do I say, the conduction band जहाँ पे है, the conduction band of the semiconductor, that point, you know, minus the point of the Fermi level of the metal.
Yes, sir.
Okay, so essentially it is the electron affinity of the semiconductor minus the work function of the metal. Okay, or work function of the metal minus the electron affinity of the semiconductor, which is not dependent on doping ideally. That's why the Schottky barrier height is not dependent on doping, but the built-in voltage is dependent on doping. Matlab, how much are you going to pull the Fermi level down? Or band bending kitna hoga? How much are you going to bend the band down? That depends on the doping very much, because that depends on the Fermi level position of the semiconductor. However, when you bend it down, the absolute value of the Schottky barrier height is not dependent on doping, because that is just work function of the metal minus electron affinity of the semiconductor. Okay, am I clear?
Yes, sir. Thank you, sir. But sir, one more question, sir.
Yes.
Sir, if I built-in potential is N side and P side same, no, sir?
Your voice is
Built-in potential is same for N side and P side, or hello, sir, now I'm
can
hearing.
you please can you type the question? In which may I can hear you, but then I lose you.
Achha, sir, now can I listen, sir? Hello?
Yeah.
Hello?
Yes, I can hear you.
Yes, sir. Sir, built-in potential in N side and P side is same or not, sir?
Built-in potential is not
Hello?
defined. Can you hear me? Hello, can you hear me?
Built-in, yes, sir. Built-in potential is same for N side and N side. Yes, sir.
Are you talking about a PN junction or a Schottky junction?
Hello, sir. Hello.
Yeah, I can hear you.
Sir.
Are you talking about a PN junction or a Schottky junction? Hello, I lost you. Hello.
Yes, sir. Hello, sir. Now can I listening, sir? Hearing?
Can you type your question, because and so we are losing a lot of time. Many people might have questions. So
Okay, sir. I will.
Yeah.
It is listening or not, sir?
In between, I can listen, and between
Sir,
you bring on.
If one question, what about I know, sir? Yes, sir. Sir, built-in potential in pair side and N side is same, no, sir?
Are you talking about a PN junction or a Schottky junction?
Yes, sir. PN junction.
No, the built-in potential is not defined for P-type or N-type side. It is defined for the entire junction. So there will be some voltage on the P side, there will be some voltage on the N side. The total voltage drop is the built-in voltage.
Sir, one question you ask, if doping concentration in N side and P side is changed, then what is the built-in potential in N side? Sir, this question I will be very much confused. Sir, how it is look the diagram if built-in potential N side and P side is different?
The built-in potential is defined for the entire junction. It is not defined for N side or P side. However, there is a voltage dropping on the P side, there's a voltage dropping on the N side, and the total sum of these two voltages is the built-in voltage or built-in potential. Now, if the doping on both sides are equal, then the voltage dropping on both sides also is equal. But if the doping is higher, okay, if the doping is higher, you have a certain depletion width. Okay, at the junction, you have a depletion width on the N side, you have a depletion width on the P side. Okay, now if your doping is very high on one side, then the depletion on that side is very small. The depletion, most of the depletion will be on the side where the doping is light. Okay, and whenever there is a depletion width, there is a voltage drop. So if you have a lighter dope side, maybe N side is light dope, maybe P side, I don't know. Whatever side is lightly doped, your depletion will be mostly extending along that side only. So most of the voltage will be dropping across that side only. Just like if your built-in voltage is suppose 1 volt, and your doping on N side and P side are such that P side doping is say 100 times more, then kya hoga? Then most of the voltage of this 1 volt will be dropping on the N side only. Very little will drop on the P side, because usme depletion side itself is very small. You see my point?
Yes.
Okay.
And sir, another question, sir.
I can hear you. Your voice is breaking down. Can you
Sir,
please?
in very much
Can you please type the question?
Type.
Your voice is breaking now. I cannot hear. I mean, if you type, it will be more efficient. Maybe someone else can speak then or whatever. You can type the question in the chat window and I'll reply. What is periodic potential? Periodic potential is basically when you have periodically arranged atoms in a crystal, which is how it is. So each atom will have a potential around it, no? Because of the way the atoms are arranged in the way the electrons are arranged in an atom. You have these different shells, different energy level. So if you have one, atom, you have one potential around that atom. So if you have two, then you will have two different potential. Now, if you have infinite number of atoms which are arranged periodically at a fixed spacing apart, then you have potential for each of them. So that is what we call periodic potential. Now, in a periodic potential, where the potential is varying periodically, the period is, by the way, that the spacing between the atom. Then that periodic potential may you have to the Schrodinger equation to get the band and band equation and other things. Okay, so periodic potential is basically a potential which is repeating periodically. That's all.
And sir, quantum well,
I cannot hear you. Can you please type? Quantum well. Yeah, what is the question about quantum well? Quantum well.
Yes, sir.
I cannot hear you. Your voice is breaking down. What is the question? I see your point that sir quantum well. But quantum well is it's like saying sir semiconductor device. Yeah, semiconductor device. So what is the question? Are you talking about the depth of the quantum well, energy level in quantum well, how quantum wells are formed, application of quantum well? I don't know. I mean, you have to give the question now. If you just say sir PN junction, okay, PN junction question players, right? I want to know depth. Depth as in like the thickness, the physical thickness of the quantum well. It depends on the material that you're using. All about quantum well. Okay, all about the quantum well I cannot talk now because it will take long time. Quantum well basically in reality is when you have a material which a narrow band gap and it is between two material with wider band gap. So kya hoga when the conduction band, it will see a drop because the narrow band gap material is in between two wide band gap material. Okay, so essentially it's like a energy landscape. In the energy landscape, there is a dip in the potential. So it's like a well. Now the thickness of the well physically in nanometer, 5 nanometer, 10 nanometer, etc. There is a limit to which you can say it is a quantum well. If it is 100 nanometer, for example, it is not quantum well. It depends on the material. Essentially, a quantum well should be such that electrons or holes, whatever, should be able to move only in the XY plane, not in the Z direction. Where the well is confined, it should not be able to move in the Z direction. So that confinement dimension depends on the de Broglie wavelength or de Broglie wavelength as we call. The electrons are also wave. So electron has a de Broglie wavelength. You can calculate that based on the mass of the effective mass of the electron. And that depends on the material, by the way. So effective mass, on the effective mass, you have the de Broglie wavelength. If the de Broglie wavelength is suppose 20 nanometer, then your quantum well has to be less than 20 nanometer, like that. Okay, so that's the thickness or the depth of the quantum well. And you have energy levels in the quantum well which are discrete. You cannot have continuous energy. Okay, it's like the potential a particle in a box or a ball in a box that you talk about in our 10+2 undergrad physics. That's all. Okay, quantum well has many applications. Quantum well, because carriers are confined there, they cannot move in Z direction, so they can only move in XY direction. So it's like a sheet of electron. They can be very high density sheet of electron that can help you make very fast transistor. They can give rise to very interesting and exciting optical phenomena because you have discrete energy levels, magnetic phenomena. People use quantum well in commercial devices. Most of your cell phones that you have, they might also have quantum well devices, because the transistors, they might have a quantum well that needs for, signal amplification. And there are many, many applications. It's not a 1 hour topic. You can read a lot about it. You can, get so many things. I hope that answers your question.
Okay, sir. Thank you, sir.
No problem. What is the transient response of a PN junction diode? I mean, transient response means in a PN junction diode, how fast can the diode go from one state to another? From the forward to reverse, reverse to forward, turning on and turning off, turning off and turning on. How fast can this turning on, off and turning on can go? Okay, so that is the transient response. If you can switch it on and off between the forward and reverse characteristic fast enough, then it's a fast PN diode. So what are the factors that limit the transient response? So the most important factor that limits the transient response is the diffusion capacitance. That means in a PN junction, you have minority carriers which are injected from N side to P side to N side. So those minority carriers get stored as a charge in the neutral region, quasi-neutral region. So every time you switch on the device, for example, it means a forward bias you're applying. Heavy current is flowing. So a lot of electrons are going to the P side, a lot of holes are coming to N side. So these minority carriers are getting stored in the neutral region on both sides. Now, if you switch off the device, if you suddenly go back to reverse bias, then this stored charge has to discharge. You have to dissipate this charge away because the diode has to turn off. The depletion has to widen. So this discharging of this entire charge takes some time. It's a diffusion capacitance. Okay. And again, when you turn on, again, the diffusion capacitance you have to charge. So the rate at which you are supplying the charge, rate at which you are taking the charge away, the diffusion capacitance will determine the transient response. There's a lot of equations, it's called the charge control analysis. A lot of equations will come in terms of the diffusion capacitance, long diode, short diode, and things like that. But those will determine the transient response. And typically transient response have this very classic shape, and they are slower than a Schottky diode, for example, because Schottky diode, there is no minority carrier. So Schottky diode can turn it on and off very fast. There's no limit to the diffusion capacitance. Minority carrier charge storage is not there. Okay. So I hope that answers your question.
सर फॉरवर्ड बायस में डिप्लीशन लेयर श्रिंक होती है, तो क्या कोई इतनी वैल्यू होती है क्या फॉरवर्ड बायस की जिसके बाद डिप्लीशन लेयर गायब ही हो जाए?
Good question. So you're not talking about transient response. In general, you're talking about a forward bias only, right?
Yes, sir. Yes, sir.
Okay. So forward bias, what happens is that the more you apply forward bias, the current exponentially, which means for a very small increase in forward bias, you have a huge increase in the current. Now, when your current keeps increasing, then what will happen is that you will go into a high injection regime. Okay, the usual PN junction equations that we talk about are all low injection, because the amount of electrons that I'm injecting or the amount of holes that I'm injecting is very small compared to the background doping that I have. But if the current increases significantly, then the high injection effects come into picture, which means the number of electrons or holes that I'm injecting is so high that it is comparable or more than the background doping on the other side. In that case, all the equations that we derive break down. We have to modify the equations. Okay, the ideality factor will change, and secondly, there will be a lot of heating effects will come because high current is flowing. And then the neutral region that we talk about are no longer neutral. There will be a lot of voltage drop in the neutral region. Okay, there will be a lot of voltage drop. There will be a lot of heat generated. Then a lot of series resistance will come into picture. Whenever there is a voltage drop, there will be a resistance that will come into picture. So that series resistance that will come into picture, plus the heating, plus the non-ideality that will come because of high injection effects, all these things do not, what these make is that they make the existing equation invalid. So we cannot think of a depletion region in the conventional sense. Okay, it becomes small, but then you cannot say it has completely become zero, because the huge number of, so ideally when we say we are applying some voltage, we assume that the entire voltage is dropping on the depletion region only, the built-in. But that is not true when you have very high current. Most of the voltage will now drop in the quasi-neutral region, in the contact region. So the voltage will not even reach the actual depletion, the built-in region. The huge current will flow, heating will happen, and everything else will drop the voltage. Okay, so we cannot just say that the depletion will become zero. So someone said, what was the question that Hani Sharma just asked? I cannot understand Hindi. The question he's asking is, in a forward bias PN junction at sufficiently high bias, will the depletion region become just zero? That was the question, and the answer I had just given. I hope you can understand that now. Okay. I usually try to answer that answer in English so that everyone can understand. But yeah, if you can ask in Hindi. If you're comfortable, I can translate it in English, the question, and I also answer in English as well as in Hindi. Okay. Syed Shabir Bukhari, how about research internship in hot topics of semiconductors and devices? I don't know. Hot topic is a very qualitative term. Many things can be hot, many things can be cold. Research internship where? It depends on the individual advisor that you are looking at or individual faculty member. There are many faculty members in IITs, ISC, TIFR, ISAR, even NIT. You can mail them if they have opportunities. They will tell you. In this session that we're talking about is NPTEL for the course. Here I will not entertain questions on internship opportunities with me. Okay, this is only for question answers on semiconductor devices for NPTEL. You can ask about career opportunities, but I will not answer questions on internship opportunities with me. Okay, because this is not the correct forum for that. But you can email individual faculty members. So Bhuvanesh M, I wish you to do PhD under you. What skills are required? Again, it's not PhD under me, it's a PhD in semiconductor device. It can be any advisor. There are many excellent people all over the country in IIT Delhi, Bombay, Kharagpur, Kanpur, Madras, TIFR, ISAR, Pune. Excellent people are there with a lot of industrial connects also. You may wish to explore and talk to them, email. If you send 10 emails, you can get reply to at least few emails back. So you have to send emails that are short. People don't have time to read long email. People don't read long emails. You just have to be 1 or 2 lines. Okay, that's how you should write emails. To do PhD under any of these people in the area of semiconductor, what are the skills are required? I mean, GATE score should be good, and you should be very good in basics. At least at IISc, you are in an interview, you are asked questions to understand how much you understand. You are not asked to. You're not interviewed on equations or memorizing some things. It's about how well you understand, how well you understand the concept that you have learned. That's all people test. Okay. Syed Shabir Bukhari, what is a phonon? It's an elementary particle. Phonon is actually the vibration of the atoms in a crystal lattice. Atoms will always vibrate at any temperature. So we quantify that vibration as a phonon. Okay. You can think of it as some kind of a quasi-particle, but so it has its own, Bose-Einstein statistics that the phonons follow, the phonon distribution. There are different kinds of phonon, optical and acoustic phonons, and then they have different branches in energy. It's a whole area of condensed matter physics. You can read the books by Charles Kittel, Condensed Matter Physics. There is also another book by Ashcroft and Marmin. You can read the chapters on phonons. There's a lot of physics-based treatment there. We do not delve into so much depth in our semiconductor device course for now because we do not need that. I mean, that's more advanced. If you want to understand transport mechanism, if you want to understand the details of the mobility and the electron velocity, how they are derived, what are the implications, and if you want to work on the in the physics side of the devices, that is, when there's a new semiconductor, when there's a new heterostructure, you want to find out how the new material has different kind of phonons, metal atomic vibration, how electron mobility or velocity at different temperatures, different electric fields, they're modified. You want to understand the physics of it. You want to write equations. You want to do modeling and simulation. Then you need to study more about phonons. Okay, but in general device design, we generally understand the basics of phonon. That phonon scatters electron. How does it scatter electron? That it sets up an electric field. The electric field perturbs or disturbs the electron when it moves. It's not physically hitting the atom. It's the atom vibrating that sets up a field, and the field will scatter the electron. So you have to, that is the basic idea. But in advanced form, you have to write all kinds of quantum mechanical equation. You have to write a Hamiltonian, you have to write a Fermi-Golden rule. There are many things are there. We don't discuss about that. Okay. Some of the very famous professors in US include those in Purdue University, Professor Mark Lundstrom, Supriya Datta. They are very old by the way now. Professor Saif Salahuddin at UC Berkeley, I guess. And there are many people. You can check their website, their papers, their books. You'll get a lot of idea. Okay, there's another question, Anupam Jena. Without compromising collector current and gain, how early voltage is to be changed high? So if I understand the question, you are asking how can the early voltage be high without compromising the collector current and gain? So what is early voltage? Early voltage? Sorry?
Yes, sir, this question I asked.
Okay, so early
Nothing, sir.
Yeah, so early voltage is that, if you have that in the BJT, the collector current, output current will have a slope, and that will, if you extrapolate, it reaches an early voltage. Why? Because the collector voltage, when you change it will deplete the base a little bit more, no? So the base thickness changes like this. The more the base thickness changes, the more the slope will be. So you want ideally the early voltage to be infinite. It should be very, very large. So there should be no slope, which means when you apply collector voltage, the base width should not change. It should remain constant. So for that, your base doping has to be very high. Your base doping has to be very high so that the base depletion doesn't change with collector voltage. If your base doping is very high, then what will happen? If your base doping is very high, then your gain will become lower, because your gain is the ratio of the emitter doping by base doping. So it means if your base doping is very high, your gain will become low. To increase the gain, you need to increase the emitter doping also. But if you increase the emitter doping very high, then emitter band gap will reduce. A lot of problems will come. So it's basically a design engineering. It's a design space. You want to have a little bit of early effect. I mean, because if you do not want any early effect, then your gain will be no gain. What is the point of having a device where the early voltage is very good, but the gain is nothing? So you want to sacrifice a little bit. You want to have some kind of early voltage, high early voltage, maybe minus 50 volts, minus 30, minus 100 volts, something. Some early voltage is there in the base which is changing. But for that doping, you can get a higher emitter doping with some gain. Okay. And in the circuit designing people do not depend entirely or do not depend on the accurate value of gain, because gain can fluctuate very quickly. Depending on the current, depending on the base doping, the thickness, lifetime, and all, the gain can suddenly change. And you do not want to design an analog circuit or mixed signal circuit around a parameter like gain, which is very susceptible to change. So people do not depend on the accurate value of gain. They depend on a range of gain. The gain should be high. So gain should be more than 20 or more than 40. If the gain is more than 40, I'm happy. My circuit design will not be affected. Okay. The people look at that only. They don't look, my gain has to be a 35, not like that. Okay. So there's always this trade-off. Another question is Ajay Jadhav, career opportunities in electronics after BSc or MSc. I mean, if you are doing a BSc or MSc in electronics, it's good to probably do MTech if you can. If you feel like, or if you can, then with an MTech it becomes better. But electronics is a very vast area. Semiconductor device is only one part. There is analog, there's VLSI, digital VLSI, there's signal processing, image processing, there's communication system, there's control system, there's power system. They are very electronics is very vast. I don't know what you're talking about, which area, but in general, electronics is a lot of option. People in communication system, signal processing, they have different companies, different jobs. Image processing, they have different job. Analog mixed signal design have different job. RF microwave electronics, that's a complete different job. Antenna design, so many cell phone companies are coming up. So those are different areas. I mean, this huge ocean. Electronics has many options. Okay. If you are really good, you will be in demand. Okay, you will be in demand. It's not electronics. To become an expert in electronics is not very simple. Just learning like just some coding or something. Okay, I'm not saying computer science is easy. Coding is not computer science, by the way. But I'm saying you need to have that kind of training, that experience to become really good in electronics. And once you have that, then you are valued. It's very difficult to get that very quickly. Okay. So someone is asking Passam Kiran Teja, at high forward bias voltage, their voltage drops is highlighted by you. Is this a model of the real process, or the real process actually high field velocity saturation? High field velocity saturation is when you have very high electric field. Okay. It does not necessarily have to be high current. High velocity saturation does not mean high current, by the way. You can have few electrons, just a few electrons that are moving at velocity saturation, because the field is very high field and very few electrons are moving. So you'll have less current because the current electrons are very few, but they're moving at velocity saturation. So that's a different concept. This high voltage bias in a PN junction, it need not be at velocity saturation, but the number of carrier is very high. So the current injected is super high. There's a lot of heating and a lot of voltage drop. Okay. It does not necessarily mean there's velocity saturation, because velocity saturation has to be very high field across a very small region. You may have a very large voltage drop across a very thick region. So the field may not effectively be very high, but the carrier density that you're injecting may be very high. So that even a small field leads to super high current. This has nothing to do with velocity saturation. Okay, I hope I could answer the question.
Sir, जैसे सोलर डिपेंडेंट एनर्जी हम सोलर सेल में यूज करते हैं, वैसे क्या टेम्परेचर डिपेंडेंट इलेक्ट्रिसिटी पे काम हो रहा है क्या, कि टेम्परेचर से हम एनर्जी जनरेट करें?
The question is, just like in solar cell we are converting light to, your question is, are we converting heat to electricity? Am I correct?
Yes, sir. From temperature, like room temperature in summers, we can use temperature difference to create electricity.
That electricity that you generate from temperature difference in general is very low to be of meaningful significance, but people do use it to make sensor. people, the sensors that you have, temperature sensors or some kind of, humidity sensors and other things, those sensors need very small current. So they use the temperature difference to generate electricity to make sensor. But that is not a useful electricity because the amount of electricity you generate from temperature difference is very small. You may use this Seebeck and Peltier effect kind of thing. For a huge difference in temperature also, the current is very small. If you have only few degrees Celsius difference, then the current is negligibly small. You can make sensors, nothing beyond that. That being said, people have used that to demonstrate that people can use recycled heat, at room temperature. You have very high temperature outside, very low temperature inside. People have done that at demonstration. India's defense lab also has done that. I think many companies also have done that. It is not sustainable. It is not profitable because the amount of investment and the things that you need to make that is far more than the amount of returns that you would gain. Okay, so many people also try the industrial waste plants that have, they have a lot of temperature, high temperature fume, high temperature chimney, high temperature waste. So can we have this electronics around it so that the extra temperature difference with the room temperature or the atmosphere temperature can be converted to electricity? Yes, you can. People have shown that. People have used that electricity to light an LED, but it's very, the amount of effort that you need, amount of money that you need to set up the whole arrangement is so high that it doesn't make sense because the amount of electricity that you're going to get out is very tiny. Okay.
सर बेसिकली हम उसमें क्या यूज कर रहे हैं? हम पीएन जंक्शन यूज कर रहे हैं, हम ट्रांजिस्टर
क्या
यूज
this Peltier and Seebeck effect. You have these materials that can have this electrical high coefficients of Peltier or Seebeck effect. Okay, you cannot use a PN junction because PN junction will not give you any appreciable current with the temperature difference. It's like any material or many of the specific materials have this Peltier and Seebeck effect. If you recall what I'm talking about, any temperature difference creates an electricity, but that electricity is very tiny. It's practically not useful. Now the next question is in EB transition delay. What is EB transition delay? Emitter base?
Yes, sir, emitter base.
How does saturation velocity depend on forward voltage? Saturation velocity. There is no saturation velocity in EB transition, no? I mean, for saturation velocity, you need a very high field. A base emitter is not at very high field. A very small voltage you apply. So there is no velocity saturation on EB junction. There is velocity saturation in base collector, where the depletion is wide and the field is very high. The only but emitter base junction there is no saturation velocity. Okay.
Then sir, you asked one question: when emitter base voltage increased by 50 millivolt, then how the delay time change?
The delay is different. The delay is concerned with the base emitter.
The transition delay is depletion width divided by saturation velocity, no sir?
That is only for the base collector depletion width, not the emitter base depletion width.
Sir, emitter base, there was some charge particle delay, not the
emitter base is basically the capacitor charging delay. That's
yes,
all.
Sir.
That's
not
all.
Transition delay. Then you asked what is the emitter base transition delay?
I have to look into the question, but emitter base is the capacitor charging and discharging delay. If I'm asking that, transit delay is generally the delay through the base. Okay, base collector has this depletion divided by 2 times velocity. That comes only in base collector because that is a huge depletion width.
Sir, one question you asked: what is the base emitter transition delay? That's why I get confused. I know base emitter is only charge particle delay. What? There's not transition delay.
Base emitter transition delay. I said this question
Yes,
long back. I don't remember, but base emitter delay is the capacitance delay. So you have to calculate the capacitance delay only. But I mean, I don't understand what base emitter delay. See, base emitter junction does not have this depletion divided by velocity. Just has a base emitter capacitance delay. Okay.
Yes, sir.
सर जैसे सोलर सेल का हमें पता है कि सिलिकॉन उसमें कैसे काम कर रहा है, तो सर पेरोस्काइट जो मटेरियल है उसका आप थोड़ा फिजिक्स बता सकते हो, मतलब ऊपर से?
Physics though I don't know much. I don't work on perovskite. These are research topics. You can contact Professor Shusho and Avasthi at sense or Professor Aditya in general. Not as a part of NPTEL, but in general. Perovskite is a more emerging and a new class of material. People are still investigating them. There's all kinds of different perovskite. I don't know the chemical composition. Okay, it's a long equation. Halide perovskite, and they have this. Sometimes they have the lead containing compounds. some are lead free. This you can actually make very easily, like spin coating, and taking a liquid and then spin coating it, spinner. It's very easy to make large area, spin coated. You don't have to go through the extensive fabrication in silicon wafer, it's very costly silicon wafer growth. So perovskites have been found to give very high efficiency in solar cell. Very quickly they got very successful. However, there are many issues with perovskite. I think reliability, long-term operation, long-term degradation, and also at high temperature. If you put it on the rooftop, can it sustain over day in and day out? And so large area, and many other challenges are there. But it is being
efficiency ज़्यादा है उसकी शायद.
Yeah, as I said, its efficiency is more, but more as in like it's comparable to that of silicon. But you don't have to spend much money. It's very simple. It's very, very cheap. Silicon wafers fabrication takes a lot of time and money. So perovskite is very cheap. It can make low cost, affordable solar cell. However, reliability and other degradation problems are being investigated. Okay. There's a question in current flow, whether the electrons are moving from point A to B or they're bound to each other. Bound to each other? No, electrons are moving, no? They're physically moving. What do you mean bound to each other? Bound to each other? No, electrons are not bound to each other. Electron holes can be bound together. Sometimes they are called exciton. But those come in optical devices. Electrons and holes that are bound to each other.
सर जो मैटर का वर्क फंक्शन होता है वो जब हमने फोटो इलेक्ट्रिक इफेक्ट पढ़ा था क्लास 12th में, तो सर वो इलेक्ट्रॉन को मेटल से बाहर लाने के लिए एनर्जी को बोलते हैं, या फिर वैलेंस शेल से बाहर लाने के लिए जो एनर्जी लगेगी उसको वर्क फंक्शन बोलेंगे?
Work function is from the Fermi level of the metal. Metals do not have band gap.
ओके सर, तो सर जो इलेक्ट्रॉन वो किसी शेल में ही होगा ना मेटल की, तो वो उस बॉडी के अंदर ही आके फ्री इलेक्ट्रॉन बनेगा या पूरी मेटल से ही बाहर आ जाएगा?
Photoelectric effect.
यस सर.
Photoelectric effect, electrons will come out.
बॉडी के ही बाहर आ जाएगा.
Photoelectric effect में electrons will come out of the metal.
तो सर ऐसे तो अगर हम कंटिन्यूअसली लाइट डालें उस पर, तो उसका तो मास ही खत्म हो जाएगा मेटल का.
No, electrons do not constitute the mass of the metal. No, atoms constitute. Atoms don't come out. No.
अच्छा, तो सर मेटल पे चार्ज तो आ जाएगा.
They will also get screened out. Metals cannot sustain field, so they will keep screening. Metal is like an infinite reservoir of electron.
Okay, sir.
Sir, one question, sir. Sir, in heterojunction bipolar transistor, what is the facilities compared to BJT, sir?
So in heterojunction bipolar transistor, you can use material of different band gap. So typically people use an emitter of a higher band gap and a base of narrower band gap. The advantage is that, as I told you, the gain of a transistor depends on the doping of the emitter divided by doping of the base. So in the BJT, normal silicon BJT, to get a high gain, your emitter doping has to be much higher than base doping. Okay. But base doping cannot be low, because if the base doping is low, your early voltage will be really bad. And secondly, the base resistance will be very bad, and those will affect your performance. So because of these two reasons, the base doping cannot be low. The base doping also should be high. Now, if the base doping is high, the emitter doping has to be even much higher. And at such high levels of emitter doping, the emitter band gap will become smaller, because high doping can lead to smaller band gap. If the emitter band gaps become smaller, then all kinds of problem will come. Okay, then your gain will even become much lower. There will be no gain. The gain will be less than 1. There is no gain. So when you have a heterojunction bipolar transistor where the emitter band gap is larger, what happens is that even if you dope the emitter extremely high, even if the band gap of the emitter becomes small, slightly small, still, because of the wider nature of band gap, it is still larger than the base. And because of that, you can dope the emitter as high as you would like without thinking of the problem of band gap narrowing, because the band gap narrowing will not affect it, because the band gap is already very large. Okay, so it means you can dope the emitter as high as you want. That means you can have very high gain. That is point number 1, because you don't care about band gap narrowing anymore, because the band gap is very large. The second point is, in a BJT or even an HBT, the base emitter junction is forward biased. So the base, if it is p-type, for example, NPN, the base will put some holes into the emitter, back injection. These back injected holes from base to the emitter are useless because they do not contribute to the collector current. They come out from the emitter. Now, if you keep a heterojunction bipolar transistor, then the band gap difference between the emitter and the base will create an energy barrier which will prevent the holes from base to come to the emitter. Okay, that will prevent the holes from base to come to the emitter. That will improve the gain even more. That will improve the gain even more. It's like you think base is supplying some water to the emitter, and this water is useless. It doesn't go to the output. It doesn't go to the people who need it. It comes out to the emitter only. So you put a barrier. The wide bandgap puts a barrier so that the water from the base cannot come out to the emitter. It's blocked. So it's helpful. It improves the gain. So these are two main advantages of HBT over BJT. I hope that is clear.
Sir, each early voltage is shrink in HBT
Voltage
compressor.
in HBT. In HBT, the early voltage depends on the base doping and the collector doping. If your base doping is light, then the base collector depletion which will push the base, so that will lead to early effect. So in HBT, typically the emitter is larger, but the base collector is not so much. I mean, they are similar, you know. There is some graded layers and other things, but not so different. Only the emitter is wider. So in HBT, the early voltage problem is not so much different from than in BJT. But however, you can actually dope the base high. Okay, you can dope the base high and dope the collector very light. And then after that, there's a highly doped collector. It's called a subcollector. Okay, so that way people have kind of people have kind of engineered the early voltage problem. In BJT is a bit more problem because you cannot dope the base super high because the emitter doping has a problem. In HBT, you can dope the base very high because the emitter can be still much higher. And so your emitter, your early voltage problem can be also mitigated to a significant extent.
Then it compress or not?
I didn't understand your question. Can you write it down?
So can I listening so here, sir?
I can hear in between.
Hello.
Please tell me.
Sir, in HBT, VP early voltage is compress or not?
In HBT, early voltage is also very high. It should be ideally very high, minus 50 volt, minus 100 volts. So in HBT, yeah, it is very high. It can be minus 50 volt, for example. Assam Kiran Teja is asking, in BJT, there is back injection from base to emitter in forward active mode, as we know, but the amount of hole doping in base is finite. Does this mean holes will run out in concentration? No. When you're operating the device, no, whether BJT or MOSFET or whatever LED, doesn't matter. When you're operating the device, no, you have the connected terminals, base terminal, emitter terminal, collector terminal. Those terminals will supply electrons or holes as the case is. So they will not run out of hole. The base will not run out of hole because the base current is hole. The base metal contact is injecting hole. Okay, so you will not run out of holes. Okay. Then there is this question. Eventually, we'll run out of holes in concept. No. They will not run out. You are injecting holes from externally from the bias. Okay. No. It does not affect the shelf life. Holes will not run out. It's not like that. In a MOSFET, it's not like your electrons will run out of the channel. Okay, or the N+ doping. It is not like that. Sir, course notes are not provided. I do not have course notes. I mean, I taught everything from memory and I wrote down the whiteboard. So the recordings whatever I wrote down are actually the notes. Okay. If you have any question, you can always email me. I try to reply promptly. Okay. So if you have question, you can email me always. Manish Bhai is asking, sir, hello, sir. आप diploma student को पढ़ाते हैं? He's asking, do you teach diploma student? I teach as in like I work at IISc, and IISc, it will depend on IISc policy, whether IISc admits diploma students or not. I don't know that, okay? That you have to check with IISc administration. But in general, if you ask a question, I'll reply. It doesn't matter whether you're doing PhD or diploma or high school. But if you ask me a question in email, I'll reply. I cannot teach a separate course one-on-one on separately. If you are a student, you may be a diploma, you may be PhD, I don't know. But if you want me to teach a course to you one-on-one, that is not possible, of course. But in the NPTEL, I do offer these lectures, and you are free to listen the lectures and learn, and have questions. You can always email me. My email ID is there. So that's how it is. But in ISC, can I teach diploma? You have to ask the institute. I do not decide the admission policy.
सर आपकी रिसर्च का फील्ड क्या है सर, मतलब सर थोड़ा बता सकते?
My research is in semiconductor, gallium nitride and wide bandgap devices. Okay.
Okay, sir.
Hello.
This forum or this session is for NPTEL, semiconductor device question answer. So I try to avoid answering questions on my own research and my group and other things. Okay, it is about semiconductor devices. Is there opportunity of undergrad in your research groups? I'm sorry, I will not answer that question, because this is only for answering semiconductor device question. So any questions regarding my research, my opportunities, I will not answer, unfortunately. Okay, you have to email separately.
Good evening, sir. Good morning, sir.
Mhm.
I have a doubt regarding the contacts, the metal contacts with semiconductor. So how does either of the contacts, say ohmic or Schottky, how does the current through those contact junction contribute to the current in the circuit as a whole, practically?
It's a junction. The current electrons will flow across the contact. What is the problem?
No, so like practically we have, say, a PN junction in the circuit, and there's a source attached to it. And at the same time, we are having these metal contact junctions on the ends. So how do the current through them would contribute to the net current in the circuit?
Oh, I'm not getting the question. See, if there's a contact, there's no problem. Electrons will flow from the contact to the semiconductor. No? The current has to be continuous, Kirchhoff's law. So there cannot be any accumulation of current. So I understand current is flowing in the wire, then it sees the metal, then it sees the n-type semiconductor. So it goes across the junction. It's an ohmic contact. Even if it's a Schottky contact, depends on forward or reverse bias, there'll be a voltage drop across the Schottky contact. And that's how it is. The contacts will drop some voltage. You want the voltage drop across contact to be as low as possible in general. So it's just like any other resistor. You can think the contact with the semiconductor can be modeled as a resistor. It's called contact resistance. So you just model it as a contact resistor, then it's easier.
Okay, sir. Understood, sir. Thank you, sir.
Yes. Here, no more questions. No more questions. I'll wait for a few more minutes. Career opportunities, I have mentioned that, Ajay Jadhav, that electronics is a vast topic. Goes from signal processing, image processing to analog mixed signal, RF, microwave, semiconductor device design, control system, power electronics, many things are there. So depends on what area you're talking about, but there are many opportunities. It depends on what is your specialization. If you're an analog mixed signal or digital, there's a lot of fabless houses, companies that will need designers to design the front end or the back end. If you are microwave and RF electronics, then there are, of course, many opportunities. Many cell phone and broadband companies are coming out. If you're a control engineer, if you're power systems, then of course there's so many power plants, and power electronics is a very big topic now. Design power converter. So there are many opportunities, but you have to be really good. Only the coursework is not sufficient. You need to get this extra training. You need to get some experience either in internship or do some extra courses. And if possible, do an MTech, at a good institute, so you get some hands-on experience. All these things matter. All these things will help you get, and the experience build matters. Okay, in this area, experience matters a lot. So you need to prepare yourself accordingly. But electronics is a vast topic, and semiconductors is only one aspect of it. Okay. We have 4 more minutes remaining. Any question, please bounce it off here. No question. Good for a few minutes. Someone is asking.
In YouTube also question flows are over, sir.
There is no other question. So should we wrap up, end the session?
Yes, sir, we can.
Okay. Thank you, everyone. You can still email me.
Thank you, sir. Thank you, sir.
Thanks. No
Thank you,
problem.
sir.
Take care.
Okay, sir. I'll end the session.